You have fallen into Event Horizon with John Michael Godier. Joining John today is Dr. Jun Ye. Dr. Jun Ye is a principal investigator of the Ye Group and a fellow at the Joint Institute for Laboratory Astrophysics and a fellow of NIST. Dr. Ye's research focuses on the frontiers of light-matter interactions that include precision measurement, quantum science, ultra-cold matter, and frequency metrology. Dr. Ye is a member of the National Academy of Sciences, a fellow of APS, and a fellow of OSA. He has co-authored 380 scientific papers and delivered 600 invited talks, as well as received numerous awards and honors, including the Mises Quantum Prize, US Presidential Rank Award, and others. If I may have your attention, I recently learned of some rather interesting statistics about a new type of investment. Good data is important in creating informed decisions. So I was surprised to learn that the total wealth held in art is estimated to be worth $1.7 trillion, and there are projections for it to grow another $900 billion by 2026. This is why I want you to learn about Masterworks, a revolutionary fintech company that makes multi-million-dollar paintings investable. Masterworks itself is already valued at over $1 billion, so their future is bright to say the least. This doesn't mean to only invest in art and completely ignore other investments. That said, the numbers are quite compelling, such as the price of contemporary art. Yes, I mean physical paintings outpaced the S&P 500 by 164% from 1995 to 2021. That's why you should check out Masterworks. And getting started is super easy. It only takes a few clicks to visit the site, create an account, and browse their artwork. With how crazy the markets have become, it's a smart time to diversify your portfolio by investing in actual physical assets, such as Picasso or Banksy, that used to only be available to a select few. You could take advantage now by investing in fine art and immediately start investing in this blue chip art by clicking the link below or going to masterworks.art/event horizon. And when you do, you directly help to support this channel. Thank you.
Dr. Jun Ye, welcome to the program.
Thank you for having me, John.
Now, Doctor, you work in something that's a little bit different than what I usually cover on this show, but not that different, because ultimately you deal in time and clocks and very, very accurate measurements of clocks to the point that general relativity can be observed, time dilation, over very, very short distances. So how short of distances are we talking that these instruments can get down to?
John, when you say distance, I assume you're measuring, you mean distance between two time events, meaning we're measuring the intervals of time. And we can measure a very tiny fraction of time. For example, when I talk about fractional accuracy or fractional stability or fractional precision, it can be going down to 1 part in 10 to the 20. And that's mind-bogglingly small number. If I translate that to how many seconds over the entire age of the universe, we have about 10 to the 18 seconds. So if you can measure to a fractional uncertainty of 1 part in 10 to the 20, you're talking about measuring 10 millisecond time intervals of the entire age of the universe.
When you devised this clock, the most accurate clock ever, as far as I'm aware, how long did it take from conception to actually constructing the instrument?
We have been working on this clock for the past 20 or so years. And of course, we ride on the shoulders of giants. Many, many pioneers have worked on atomic clocks. And after World War II, people realized atomic clock is really the timepiece that we want to build because it's fundamentally giving you the time based on quantum mechanical principles. And everybody can build the same kind of timepieces because in principle, if you do your experiments right, your clock must agree with each other. And that's guaranteed by the laws of nature. So over the past few decades, we have been moving, when I say we, meaning the scientific community, has been moving from microwave-based atomic clocks to the so-called optics-based atomic clocks. The idea being, instead of a microwave, which oscillates at a few billion times per second, if we get to use optics, if we get to go to all the way to the visible spectrum, where your eye can see, the electromagnetic spectrum waves is oscillating at a million billion times per second. And if you can capture every single cycles of these oscillations within a second, your measurement precision improves quite significantly compared to what you measured based on microwave oscillations. And that's really the underlying principle of the so-called new generation of atomic clocks based on optical atomic clocks. And we use lasers to communicate with atoms. Essentially, we are driving electrons between two orbits as they circulating around the nucleus. And by matching the laser frequency precisely to the energy difference between two electronic orbitals in the atom, we can use the essentially electronic oscillations inside the atom to tell us the time through the laser. And so it takes a few different innovative pieces of technology to be developed over the past couple of decades to be able to use lasers to communicate with atom precisely and then read that information out from optics all the way down to the microwave, where you can use modern electronics to count the waveform. And so this whole process really involves many of the modern pieces of technology and science, and it's been taking decades in the making.
Now, you work in ultra-stable lasers. How does that play into this timepiece?
Yeah, so this is going back to what I was just describing. In order to be able to communicate with atom, that supposedly you have a way to get this atom excited when the electron is oscillating back and forth between its two orbitals around the nucleus. In order for me to read the information out of this atom, I need to send in this laser where the frequency can be matched to the oscillation frequency of the electrons moving around the nucleus. And because the atomic clock we're chasing with such a high precision and accuracy level, we want to keep the atom being in so-called quantum coherence. When you excite the atom into this electronic orbital oscillating back and forth, we call it quantum coherence or atomic coherence. And this can be exceedingly long. In our experiment, for example, we can actually now realize nearly 1 minute long quantum coherence, which is coherence per position of electrons in these two orbitals back and forth oscillating. And for a laser to be able to read that information out, you need to keep the laser phase to be also that stable. Otherwise, you would be, it's like having a very, very noisy oscillator is trying to read something out from a very stationary oscillator. You wouldn't be able to read out the stationary oscillator. You would just be reading out noise. So we need to build world's most stable lasers with its phase and the frequency being stabilized as much as you can, where the coherence time can also exceed quite a few seconds, tens of seconds, to be able to match with atomic coherence that we want to read out to build our clocks.
Now, I take it that the atom involved here is strontium. If so, why that element?
Yeah, that's an excellent question. Why strontium? Well, strontium, as we call it, it's part of the so-called group 2 in the periodic table. What group 2 means is that it's got 2 valence electrons outside of the electronic, the outermost atomic orbital. So you have these 2 valence electrons. The electron carries a spin half, and they can pair up to form spin 0. You can imagine the 2 electrons, one spins up, one spins down. and they form a perfect match, a perfect pair, where the total electronic spin of these two electrons is 0. And turns out, when you have these two electrons paired up with each other very, very well, they're sort of less sensitive to the environmental perturbations. So atoms like that will allow you to build a system that is less sensitive to magnetic field, less sensitive to other light that's shining onto these atoms. It's less, basically you want a system to be as little sensitive as possible to the external perturbations. Only when you shine your own laser that you want to go in there and say, electron, please make a transition from one orbit to the other, or create a quantum coherence of a superposition, then the atom will listen to you. But other than that, you want the atom to be not sensitive at all to the external perturbation. That's, of course, idealistically speaking. And in fact, in the majority of the work of making atomic clocks like this is to figure out how these atoms are still sensitive to the external perturbations and to remove these perturbations from your measurement.
What room is there for successors? Can you build an even better and more accurate atomic clock from here?
Oh, absolutely. I think actually we are very positive that we will continue to move the frontier of clock making forward. As you were asking me earlier, how long has this process been from the concept, the development of the concept to actual realization to practice? And I mentioned I've been working on this for 20 years and building on other people's work as well. And over the last 20 years, we actually improved this clock system by 5 to 6 orders of magnitude to today. And I'm still going to say that I wouldn't predict that we are going to make another 5 or 6 orders of magnitude improvement. But I'm very confident to say we should be able to make another factor of 10 improvement at least, and if not more, because I don't see a fundamental limit to us yet. And as we improve on these clocks, it's actually from fundamental scientific point of view, it's actually very, very exciting because now we are starting to see gravitational redshift, or you may say gravitational time dilation at a scale of a millimeter. And this, if you improve the clock by another factor of 10 or 100, potentially we will be able to see the time dilation effect over a distance of just a few microns, 10 micron. And that's going to be really exciting because a few microns could be the distance where a de Broglie wave, a quantum mechanical wave of an atom that would extend over. And if I can measure the time being different due to the gravitational potential of the Earth at that length scale, then that means I can study quantum mechanics in this curved space. If I build coherent superpositions of multiple atoms spanning that kind of a spatial distance, I will be able to watch how the gravity actually decohere quantum superpositions. And that's a subject that has deep meanings for us, where quantum decoherence comes from, how the gravity that describes the macroscopic scale of our world connects to very microscopic side of our world described by quantum mechanics.
And I will have to reiterate that is beginning to sound like a way to get an insight into a quantum theory of gravity, right? Which is very fundamental.
Yeah, and I need to make a clarification. In modern physics, there's this big tension between quantum mechanics and gravity. And people, of course, have proposed all kinds of theory, and including Einstein and Steve Hawking and so on. They have worked their life effort to try to understand or unite quantum mechanics and gravity. And in fact, in the middle of the black hole, that's what people believe, so-called quantum gravity will arise, where a gravitational field will need to be quantized. You will have so-called graviton and so on. Super exciting stuff. The clock measurement is not going to touch that in any foreseeable future. What I'm talking about is not really verifying quantum gravity per se, rather to be able to explore a yet unexplored regime in physics, which is how do we unite general relativity with quantum mechanical wave function descriptions of atomic physics, how quantum coherence, how quantum entanglement, and so on will be impacted by the fact that the universe or any massive bodies like Earth creates space-time curvature, and which allows the universe to find out where the atom is located. And so that aspect, not quantum gravity yet, but the aspect of being able to study quantum mechanics in curved space-time is something that we will be excited of entering maybe in the coming decade.
And that in itself is an entirely new field, right?
Yes, that's right. Yeah.
Now, if you were to say to, students today that are looking for an area of physics to go into, is this one that holds a huge amount of promise?
Oh, I certainly am personally very excited, and all the students and postdocs I work with, they are all very excited. And I can tell you why this is exciting. One is, in order to set new frontiers in measurement science, really this is coming from being able to control quantum systems. And when I say quantum systems, when I'm talking about increasingly large-scale quantum systems, to the level where we can precisely synthesize or engineer quantum states, control the quantum evolution, and do very precise readout after the quantum evolution of the system. If you can do that atom by atom, photon by photon, well, you have this amazing technology then to be able to manipulate a large-sized quantum systems to fulfill the goals, whether it's for precision measurement, for sensing, or for information processing. People talk about quantum computers. You have heard about quantum information, quantum communication. In the end, all these different scientific frontiers of using quantum systems to either processing information or communicate with distant friends, or use this to measure the changing Earth, they are all connected to this fundamental technology. And so from that perspective, I find working on the problems like this, where you're trying to see how far we can go as a humankind, as a whole society, how far we can push that quantum technology. And then as we do that, there will be a lot of practical applications coming out of this, whether it's for supercomputing or whether it's for being able to explore the most advanced networks of communication, navigations, and so on. But also will allow you to peek into the unknown futures of some of the mysteries that's still out there in the universe, using these quantum physics, connecting to gravitational physics, and so on, understand what's out there as dark matter, what's out there in the form of matter-antimatter asymmetry, that we know that physics theory as a whole is not quite complete yet. And the more sensitive instruments we can build, the more likely that we'll be able to make fundamental discoveries in the coming years.
Now, to get deeper into applications and applying these clocks, now there's some history here, a long history of clocks and science and how to use them. And I think most famously would be the Harrison chronometer, where we were able to dramatically improve navigation simply by having a timepiece that could be used at sea. So we're sort of still in this in a modern age, in a modern sense, in that you could apply very, very, very accurate clocks like this to all sorts of things. So what can you do in science? I mean, what could we do to improve our understanding of science outside of physics with this?
Yes, you're absolutely right. The clock for navigation is a very compelling case of the so-called applied side of the timekeeping. And the modern example is, of course, global positioning system, GPS, that we use every day now. And when the clock, one of the key challenges of how do I move the scientific apparatus from laboratory like ours into the field so that people can actually start to apply them, is to do really incredible engineering work. And that themselves, doing this top-notch engineering itself is a big scientific challenge. It's not just, let's pack up what's being done already and reduce down to small package, and we'll have a clock that can be portable or transportable and we can use in the field. That's not going to be necessarily true. We will have to do actually really top-notch engineering research to be able to put them into smaller packages so that we can keep that level of precision and accuracy as we deploy these clocks as a portable or transportable units. If we can do that, and they are lying in lots of opportunities. If there are young people listening to this, there are a lot of opportunities to reduce from science to engineering or use engineering to benefit science. And so there's back and forth. There's a lot of work to be done there. Very exciting on its own. Once you can do that, of course, you can build network that is far superior than the current GPS. Well, what if we are going to land people on Mars or explore the entire solar system? Well, we need a GPS like that. That's certainly useful for the entire solar system. We needed those advanced clocks. What if we want to use the clock to look inwards towards the Earth and keeping us monitoring the changing Earth in a most precise way? For example, since space and time is connected, as we know that the presence of a mass can bend the space-time curvature, and you can use clocks like ours to measure the amount of a mass around you. Well, you can certainly then use this to make predictions of underground mass that's moving around you by just measuring time really well, build a clock network around some volcanoes, see if the mass is coming up towards the eruption point. Or you can use this to measure how the glacier is changing, how the underground water is migrating, measure the gravity anomaly on the Earth, and so on. So there's a lot of applications on so-called relativistic geodesy and turn time measurement into a geological survey of the Earth.
That's absolutely amazing. So by measuring time dilation, you can learn insights at a precision that nothing else can do. I mean,
that is right. That's what's so fascinating about time. This concept of relativity that connects the space and time. If you can measure time so well, it tells you the gravitational potential. And then you can also measuring time at several different elevations, like we were doing with clocks, moving them by millimeter or centimeter or 10 centimeter. You can measure the gradient of the gravitational potential. Gradient just means how gravitational potential is changing. Well, the changing of gravitational potential is gravity. So in some sense, when you have a device like this, you can measure gravity, you can measure gravitational potential, you can measure the mass distribution. And especially the more precise you can make a clock, you can use this for more higher bandwidth measurement, meaning you can translate that kind of a measurement precision into a capability of measuring changing things at a faster speed, almost reflecting a real-time monitoring of something that's changing. And that would be amazing. I think we would need more tools like that to help us to forecast the disasters or understanding what is really the Earth is undergoing some changes now.
Now, manipulating the atom or an atom of strontium with a laser seems to me like that might also have some applied science applications, right?
Yeah, that's right. There are actually companies now. One of my former graduate student, Ben Bloom, he actually opened a company. He got his PhD from our group in 2015, and he opened a company called Atom Computing, and using exactly this technology of using lasers to manipulating atoms, putting them one by one into grids made by laser light. And you can create a network of atoms, having them talk to each other, have them communicate to each other, and use them to process information. So Dr. Ben Bloom's goal is to actually build a quantum computer based on these strontium atoms. And that's just fascinating. That's what I mentioned earlier, that kind of a technology being able to manipulate atoms, controlling their quantum state, controlling how they evolve, controlling how they interact with each other, and finally read them out in a precise way of knowing the evolution of the quantum system. You can use that to do whatever you want. You can use that to process information. You can use that to make a precise measurements like time, and you can use that to communicate with each other in a secure fashion.
Could you use it to assemble something, a nanotechnological machine, say? Could you actually use it to create just the ultimate in microelectronics? Does it allow for that?
That I think I would rather say, by studying these atoms one by one and understand how they interact with each other, you gain tremendous insight of how the material actually works. You can actually get down to, for example, how magnetism actually arises from the quantum mechanics. And that insights can be tremendously useful for actual material science. We're actually assembling the real atoms and so on. In our case, our atom, one by one, they assembled a fairly far apart, 1 micron apart from each other. So they are not going to be real material per se, because they only live in the vacuum and so on. But it's a quantum machine that allows you to learn a lot about the outstanding Hamiltonians that people in condensed matter physics are still trying to understand. Allow you to see quantum phase transitions, allow you to see extraordinary dynamics coming from how you tune the atomic interactions and so on. And so that type of work that gives rise to this deep insights of how tuning a few atoms and how they interact with each other can give rise to completely unexpected phenomena to arise. I think that is very powerful for material science. And there's actually a word for it in our community, in our field, called quantum simulations. Essentially, the system I'm describing to you becomes a quantum simulator that will allow you to understand a much more sort of a real to the life applied material and how they're actually working.
That's amazing. It's an insight into the future, essentially, which is sort of poetic if you think about it when dealing with time. Now, Doctor, I have to ask you a question. Now, time is something that I think fascinates all of us because we only have a certain amount of it, and it figures very prominently in everyone's lives. When did you first decide to go in that direction and study time? I mean, what was there a reason?
Yeah, I actually have to give a lot of credit to my PhD advisor, Dr. John Hall. He is a fascinating guy who does a lot of precision measurements. And I became very passionate about doing something really well with your own hands and measure something really well, better than, say, anybody else out there. And you have to build your own instrumentation. You have to come up with your own idea to be able to do something better than anybody else who have already done, right? And as I said, we are always riding on the shoulders of giants. And I consider my PhD advisor, Dr. John Hall, as one such a giant. And what he distilled in me is this spirit of, well, if I have thought about problem carefully, and I know how to make things with my own hands, then in some sense, I can explore anything that interests me. But of course, what interests me is not necessarily good enough. It has to have an impact for the society, have a good impact for the society. And so as I learned about using lasers to cool atoms, to capture atoms in the traps and so on, I became fascinated with the fact that, well, in the previous generation of atomic clocks, atoms were still flying in free space. Now we can keep them, cool them down, trap them in little light fields and so on. And it just feels like that's the right way to go to implement your quantum technology, quantum state engineering to make a better measurement. And so I started to become really fascinated from in this field of being able to precisely measure time. And I would say the initial interest comes, as you can tell, comes completely from sort of practical side of my being an experimental physicist. I just love to do experiments in the lab. But as I mature more and more, I do think now about the philosophical consequences or implications, at least, of being able to measure time so precise, especially as we continue to push the envelope. That has now become my inspiration. How do I connect quantum mechanics and a macroscopic classical physics? Because in quantum mechanics, time is completely reversible. Only in the classical physics, time is irreversible. And obviously, quantum and classical physics has a connection, and there's some boundary. And where the boundary is, depending on how well we can control the quantum system. So all of that, it makes me really fascinated. Also the time is not absolute, as relativity tells us. And so now with quantum mechanics, relativity, the understanding of how quantum mechanics gives rise to classical physics, all of that just feels like not only has tremendous technological implications, but also has some deep questions that we may use this to inspire us and really finding future scientific visions to explore our physical world, the physical universe.
Now, on this level, this quantum mechanical level, space-time, space and time are linked. But when you get down in there, it starts to behave differently, as you said, with time being reversible and things like that. Does it become ambiguous? I mean, is there a way to understand in the macroscopic world how time functions in the world of the small?
Yeah, and again, this is really the sort of the tension point between classical physics and quantum physics. Quantum physics will say if you are isolated quantum system, then whether the time is running forward or backward, you couldn't tell the difference. But in the classical world, that's because the quantum system decohere, or another way of saying, the quantum system start to interact with its bath. The bath meaning there are environment out there that information gets lost in that environment. And when information gets lost, the entropy increases. And this entropy increase is an arrow of time. Like people often ask, can I reverse the time? Can I go back? And so on. And there is this thermodynamics, the second law of thermodynamics, where entropy is always increasing. And that's because the quantum systems are always interacting with outside of their bath. It's not completely of its own. But there are people who ask questions like, what about our universe? Isn't our universe an enclosed system? How does our universe interact with other universes? We don't really know that question. So this is going to be beyond me to answer that kind of a philosophical question. But I do know deep down there is this very interesting, fascinating sort of a story of how does entropy actually start to increase when from a pure quantum mechanical system to a system that's half quantum, half classical, eventually going into the classical. And that's how time is going to be evolving. And it's impossible to reverse unless you can make every single particle in the universe you can control it. So you can run them backwards. From a microscopic point of view, that's possible, but it's just the sheer number of these particles out there and the degrees of freedom of interactions out there makes that impossible. That's why time flows in one direction. Now, the other question you talk about is time could it be fluctuating? Could it be even not continuous? That's also, proposed in the physical theory. Like when you go to so-called Planck scale, there is no continuity of time. Time becomes itself a fluctuating quantities. And that's many, many, many orders of magnitude away from the clocks we can make today. And in fact, in order for us to get there, I don't know if as a human race will ever get there. But before we go there, the first thing you will see is actually the universe itself is not a quiet place. You have black holes popping in, popping out. You have collisions between neutron stars, and all of them, you have heard the gravitational waves. They will give rise to noise to the clocks that you make. Suppose one day that as a human race, we make a clock so good that you can put it in the middle of the universe. You can hear all the echoes of the universe where the stars are being created and being destroyed. They all create ripples in space-time. And your clock won't be able to really be quiet anymore. You will always be listening to those noise. And that's many orders of magnitude away from the clock we are making today. So we have a long ways to go.
But that does open up in the future, far future, maybe never, but it does open up a probe, right, into things like gravitational waves.
Absolutely. That's exactly right.
So, about cooling down atoms with lasers. Now, can you give a brief description of how that part of the experiment works? Now, of course, if you want to cool an atom down, you just got to stop it from moving or slow it down. But how do you do that with light?
Yeah. So, the idea being that you want to shoot light against the atom atomic motion. So suppose I make some analogies that if you think of atom as a bowling ball that you're playing, and then you shoot ping pong balls against the bowling balls. And if you put one ping pong ball against it, it will bounce off and the bowling ball won't slow down a bit. But if you have somehow a machine gun that's made out of ping pong balls and keep shooting it, eventually you will slow down that bowling ball. And that what that tells you is that each time when a photon hits an atom, it actually gives a very small momentum kick. And we can measure that very well. This is not any science fiction or anything. It's a photon momentum. It's something you can measure every day. And so if you can put tens of thousands of photons shooting against that atom, eventually you can slow down that atom and make it stand still. The tricky part is, of course, atoms moving randomly, right? And what I just described is something that the atom's moving towards you. But of course, in a gas of thermal atoms, they're all moving with random velocities. So the way to do the trick is by shooting 3 pairs of laser beams from 3 orthogonal directions, x minus x, y minus y, z minus z, such that, and you tune the laser frequency such that whenever an atom is moving towards one of those laser beams, it always gets opposed by the photon momentum exchange. And you may say, well, does that atom have to worry about the laser beam that's coming from the back side? Because that will also have a photon momentum exchange. Well, here you can use so-called a Doppler effect, where if the atom is moving towards the laser source, it moves its frequency closer to the laser frequency, so that it's more likely to absorb atom from the head-on laser beam instead of from the one that's shooting from the back. By doing so, you break the symmetry between the forward and backwards laser beams, such that no matter the atom is trying to move to the left or to the right, or to the top or to the bottom, and to the front or the back, there's always a laser beam that's going to push you back. And this is a technology of laser cooling and trapping that was developed in the 1970s, 80s, and it really perfected in the 90s, when we can cool these atoms down to such a low temperatures they can even form a new quantum matter. And because of that tremendous amount of work, number of Nobel Prizes have been given out to these pioneers. For example, the laser cooling, there was the 3 notable gentlemen who received Nobel Prize for that is Claude Cantenergy, who is a French scientist. Steve Chu, in fact, was the energy secretary under Obama administration. And he's a professor at Stanford University. And Bill Phillips, who is actually a colleague of mine at the National Institute of Standards Technology. He works at Gaithersburg, Maryland. And using those technologies of laser cooling, people can create so-called a Bose-Einstein condensate. And one of the colleagues of mine, actually, his office is right across from mine. His name is Eric Cornell, and he won Nobel Prize in 2001 for that work. And my thesis advisor, I mentioned, John Hall, who I owed a lot to my intellectual growth. And he also received a Nobel Prize in 2005 for the invention of optical frequency combs with another German scientist, Ted Hensch. So you can see, these ideas and reducing these ideas to practice of using lasers to tame atoms, to control atoms, to form a new quantum mechanical matter, to use precision technologies to ask information from the atoms to serve as a precision metrology and so on, have really been quite recent. And the development has been quite rapid. It's really tells you how exciting the field of atomic molecular optical physics has been over the past few decades.
Now, my last question for you today, Doctor, is this. Now, out of every possibility, of which there are many possibilities here for discovery and understanding, what is the one thing that you hope to answer that most amazes you as a scientist? What really are you hoping to solve?
Well, one thing I really would like to go is having hundreds of thousands of my strontium atoms all interconnected, such that they provide this quantum advantage of making my measurements better and better to a point where I can measure the time dilation effect over just the one de Broglie wavelength of these atoms. I really would like to see the connection between quantum decoherence and gravity.
All right, Doctor, best of luck with your work, and I really wish you the best. This is an amazing area of science that I don't think really gets the attention it deserves.
Thank you very much, John. Actually, there is this big effort of so-called quantum initiative now, and that's getting some notoriety out there.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.